Why do people go bald?
Why are baboons' bums red?
What's a light year? Why do leaves go brown in the autumn? Why do monkeys like bananas? Why do some things glow in the dark? Why do animals not understand you? Why do my receipts fade after a year?
Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientist with me, Sue Marchant, and Chris Smith. Let's welcome from the Naked Scientist, Dr. Chris. Hello, Chris.
Hello, how are you doing?
I'm good. Now, how is the world of science with you?
Oh, very exciting. I was just reading in this week's edition of the journal Nature, there is the most terrific bit of work that's been published, and it's quite literally out of this world, and that's because it's scientists studying Enceladus, which is one of the moons of Saturn.
Oh, right.
A little bit of history here. In 1997 I sat in a talk, and a guy called John Zarnecki came to talk to us about sending probes to distant planets, and he said, we're just about to launch the Cassini-Huygens mission, which is going to take off later this year. This is 1997. It's going to fly for 7 years through space to Saturn. When it gets to Saturn, it's going to blast down this lander, the Huygens lander, which is going to head for Titan, which is Saturn's largest moon. This will give us unprecedented detail and data about this distant, far-off world, but at the same time, the Cassini probe is going to remain in the Saturnian system, collecting data about all the other amazing moons and the structure of Saturn's rings and all the other things that go on in Saturn. And one of the things that it very quickly came across in 2005 was Enceladus and what could probably be described as the biggest geyser in the galaxy. Scientists were gobsmacked to see a plume of water, well, at least they assumed it was water, going about several thousand kilometres off the surface of this moon, straight up in the air. And this geyser's something like 10 kilometres across. So it's a huge body of water spurting out from the surface of this moon. In fact, the spurt goes so fast that it ejects this contents, water and ice crystals and things, into space, and they become one of Saturn's rings. But what causes it and what's in it? That was the question that was on scientists' minds. And now they've answered that question to a certain extent, and they've done it in a very clever way. What they did was to use an instrument on board the Cassini probe, which does spectroscopy. What they've done is to wait until the alignment of the moon and this spurt of water was in just the right place so that it went in front of the light from a nearby star. So by looking at the starlight with the probe and then watching what happened to the starlight as the jet of water went in front of it, they were able to use a technique that was discovered over 150 years ago by Bunsen of Bunsen burner fame, which is that every single chemical on Earth, or every single chemical in the universe, absorbs light of certain wavelengths. So when the spurt goes in front of the starlight, when you watch and look at the spectrum of light that comes through it, you can see various gaps in the spectrum, and that corresponds to the chemicals that must be in that liquid. And what it revealed is that 90% of the liquid is water, but there's also some nitrogen, a bit of methane, and some carbon dioxide mixed in with it. So this is giving scientists a clue as to what's inside Enceladus, this tiny moon. And it also gives a clue as to what's causing this to happen, because the water is coming out at supersonic velocities. It's spurting out through a sort of nozzle structure on the surface of the moon. And that suggests that something very, very hot is happening, building up pressure like a pressure cooker inside Enceladus. And periodically this goes off like Old Faithful. Now they have to find out exactly why, but now they know a bit more about it. It's certainly intriguing, and they'll continue to study this into the future.
Gosh, that sounds absolutely fascinating. I bet they can't
wait. Can you
wait.
imagine a geyser several thousand kilometres high? I mean, if you imagine standing on Earth and you think, say, Canary Wharf or the Sears Tower or something is tall, wow, and you're talking something which can go out into space from the ground and is 10 kilometres in diameter, that's just an amazing phenomenon. I'd like to go and see that.
I think you would, yes. That's
if only you could.
Now, Andrew has called in from Cambridge. He asked Dr. Chris, how does an atomic clock work? Chris?
Yes, a very good question. Now, I was talking about Enceladus earlier and how scientists use the light from a distant star in order to work out what the composition of the jet of water was by looking for missing wavelengths. Now, what Bunsen discovered 150-odd years ago was that the reason we know the composition of our own sun, for example, is by looking at it, because the chemicals in the sun emit light at certain wavelengths, and that means they also absorb light at certain wavelengths. And what that actually means is that the atoms of those chemicals will vibrate or oscillate at certain frequencies, because light is, at the end of the day, a wiggly wave which is vibrating at certain frequencies, and different frequencies mean different colours. So that's why different atoms have these resonant frequencies, and they will absorb light and shake at that frequency. So the way an atomic clock works, because atoms have these very discrete, specific frequencies at which they oscillate or vibrate, you can use that to your advantage to use them to keep time for you. So an atomic clock is based on that principle. And the most commonly used form of atomic clock is a cesium clock. Cesium atoms, cesium is a group 1 metal. That means it's an alkali metal. It's big, heavy atoms. And what you do is you use an isotope of cesium, usually cesium-133, and you put the atoms into a tube, a bit like a fluorescent light, I suppose, which is under low pressure, and boil off some of the atoms so that they form a vapour, cesium vapour. And then what you do is to excite them with microwaves, which are very, very high frequencies. So these are microwaves running at 9 billion hertz or so, which is close to the resonant frequency of these atoms. And this means that certain of the atoms will absorb some of the energy and get excited, and you then use a magnetic field to accelerate or select out those excited atoms, and then you have a counting plate so that the accelerated, excited atoms hit the counting plate, and the computer can log how many atoms are hitting that plate, and therefore it knows basically what the frequency of the strike rate is, and that's how you work out the time, and that's how you keep time. And because these atoms absorb at these very specific discrete frequencies, you can use this as a very specific and discrete clock. And that's how an atomic clock works, and it's accurate down to, well, many, many decimal places, which means it's the most accurate way to keep time on Earth.
Wow. Thank you, Dr. Chris. And thank you to Andrew in Cambridge for his question. Mike in Colchester has called in, and he asks, if he raises a tea bag out of a cup slowly, the water will drain out of the tea bag freely. However, when he raises it quickly, the tea flow stops. Why is this? Do you know, Mike, I've always wondered that. Chris?
Well, it's because water is very sticky. In fact, it's the stickiness of water that makes life on Earth possible. But if you look at a water molecule and say you had an incredibly powerful microscope and you could make yourself the size of an electron and you could see a water molecule, it would look like a miniature boomerang. It would have an oxygen atom at the apex of the boomerang and then 2 hydrogen atoms where the edges, the arms of the boomerang are. And the reason it's that shape is because oxygen likes electrons. It's electronegative. So you have electrons bunched up on the oxygen, and you have the hydrogen atoms, which are less electronegative, and they are also smaller. So the oxygen atoms have all these electrons clustered around them, and those repel each other, pushing the hydrogen out of the way, and the hydrogen doesn't repel itself very much, and so that's why you get this kinky, bent molecule. But because oxygen likes electrons, it makes the hydrogen on the molecule a little bit plus and the oxygen a little bit minus. And when you've got pluses and minuses, if you bring in another water molecule next door, the plus bits, the hydrogen on the second molecule, will get attracted to the minus bits on the first molecule and vice versa. So as you put in more and more molecules, you can see how they all try and stick together in a sticky way. This is called hydrogen bonding. So water itself is natively and naturally sticky. Now this means that if you put your tea bag in the tea, as you're drawing the tea bag out of the water and you're doing it slowly, then the water can stick onto other water molecules and it pulls the water out of the tea bag back into the cup. If you do it quickly, though, then you can break some of these attractions and you get a sort of airlock in the tea bag and the whole thing comes out with some water intact and the water hangs onto itself. I think that's probably one explanation for it.
Chris, another one here that has come from... where's it gone? Anne. She says she was wondering whether eating very hot foods like hot peppers, etc., chilies, yes, help with a common cold. What do you reckon?
Well, my experience, having eaten some chili this evening, it was quite funny actually, because when I talk on other radio programmes on the same evening, I often do a little sort of line test before I do that to make sure that all the equipment's going to work okay and there are no letdowns. Uh-huh. And the other day I got this dial-up from Australia, and the guy said to me, "You sound really very strange." And I said, "I'm really sorry, I can't talk properly because I've just eaten a chili." And I love chili. and I bought myself this chili plant. I went to a fete or a fair, a country fair somewhere in Cambridgeshire, and there was this couple selling chili plants, and I thought, I've got to have one of those. So I bought this chili plant, and I've nurtured it, and I had one chili that ripened first. One chili. There's loads on it now, but I had one chili, so I thought, I have to eat that. So I chopped the chili off, and I thought, well, it's probably not that hot, because it wasn't sort of a Scotch bonnet top of the tree kind of chili plant. It was supposed to be a mediocre kind of sort of southern softies like me type plant. So I just took a huge bite out of this chili. And within about 10 seconds, I couldn't feel my face. So I had to try and talk to these people, saying, yes, the line is working fine. They thought they had some kind of system malfunction, but it was just me. It was the fact that I did sort of exerted or exposed myself to such a huge dose of chili that I had sort of temporary facial paralysis. But no, I do like chili very much. And the reason that chili works is that the chili has evolved to make a chemical called capsaicin. And capsaicin can lock onto a certain receptor, a chemical docking station, which is found on the surface of tiny nerve fibres called C fibres. And these are the same nerve fibres that convey pain and temperature sensation. And specifically, there are classes of these C fibres that carry hot signals. So when you put something hot on your skin or in your mouth, it fires up these nerve fibres. So when you put chili in your mouth, these nerve fibres get subverted or fooled into thinking that they're actually being exposed to heat. So it's a chemical trick that fools these nerve cells into thinking you're being burned, when actually it's just a chemical stimulating the nerve, even though things haven't got any hotter. And that's why you feel chili is a burning sensation. But if you think about it, what the reaction to burning is, when you burn yourself, the skin on your hand, if you run your hand under the hot tap by accident, for example, it goes very red. And this makes your hand swell, and it feels very hot and red. And that's because there's been local inflammation in the skin and a surge in blood flow, because the body's response to a burn is to increase blood flow and to wash away damage and to repair. And you need a high blood flow to exert repair. So in your head and neck, if your body thinks your mouth is being burned, what it does is to increase the blood flow to your mouth and nose, and as a result of that, you make more mucus. And in the mouth, that helps to protect the mouth. It also helps to repair tissue and heal tissue. In the nose, of course, what it does is give you a runny nose. And that's why when you have a big dose of chili, it makes your nose run. So if you've got a cold, sometimes if you've got the cold and it's at that kind of stage where the mucus has become very stodgy and thick, usually once a cold is beginning to clear and you've got into the catarrh stage, if you have some chili and then you boost the blood flow back through your mucosa, the lining of your nose, by eating some chili, this can make the mucus get runnier again, and it can help to clear your nose. And that's why some people say that having a curry when you've got a cold can be a good thing.
If you're enjoying Ask the Naked Scientist, then you might like to check out The Naked Scientist, our regular roundup of the world's best science. Each week we take a look at the latest science news, talk to top researchers working at the coalface of discovery, and also get our hands dirty with a science experiment that you can join in with too. So make it a date and prepare to strip down science on the web at nakedscientist.com/podcast. Time now for another question. Mike in Colchester again. He says, Chris, are you a speed reader? And if so, or even if not, how does it work, this speed reading stuff? Are you, Chris?
I think it depends what I'm reading, actually. I'm very impatient these days, and I blame the internet for that, actually, because we've become this sort of instant gratification society now where answers are at your fingertips whenever you want them. So it tends to provoke you to just get very short-tempered about things, and you say, I want the answer and I want it now, because you know you can just type it into the internet and you'll get some answers and things. So when I pick up books these days, where in the old days I would have enjoyed reading a story and it might have taken me a month or two to finish a book, nowadays I kind of feel compelled to read the whole thing and finish it as soon as I can. And I hate myself, and I find I'm a real nuisance to myself for doing that, because I'll find a really good book and then just devour it. And I was just coming back from Los Angeles this week, because we were out in Los Angeles and San Diego last week. And I was at the airport and I was wandering around and into the bookshops, as you do. And I thought, well, that looks like an interesting book. It's Nick Hornby. He's just brought out a new book, Slam. And I like Nick Hornby's books. One of his books was about a boy, and I thoroughly enjoyed reading that. I think he's a very talented writer. And I thought, well, I like his writing, I'll buy that. So I bought this book. I thought that'll keep me amused on my 15-hour flight, or whatever it is, coming back. And we touched down in Heathrow to 0-degree temperatures. At least it wasn't having burning fires like they were in LA. And my eyes were bleeding pretty much, and I'd read all 306 pages of this blinking book. So I guess I may be a speed reader. But in terms of what actually is speed reading, well, I think people skim. And what you can do is you can let your brain fill in a lot of the gaps for you. And part of what reading is, if you watch people's eye movements when they're reading text and things, they'll scan bits of a sentence and the brain will then fill in the bits they haven't read. And this is why sometimes you make mistakes, because you think you know what's coming next and your brain fills in the gaps, and then you think, hang on, that was wrong, and you have to go back and check, and you realise you've misread it. But most of the time the system works very, very well. It's the brain seeing patterns and then filling in the gaps, because when you become good at language, for example, an adult is good at speaking a language, you know what word combinations there are. So you don't have to read every single word in order to know what's coming next. And as a result, your brain can do a lot of the work for you subconsciously, and you get a seamless reading experience, but you're not actually having to laboriously read and decode every single word. And I think that's partly what speed reading is. And where you notice reading getting laborious is when you go into territory where your brain can't do that. So you start to read something very technical or something in a foreign language, and you're having to laboriously decode every single word. And that's when you notice how fast you normally go, and that's when you realise how much your autopilot in your brain is normally doing for you.
Chris, it's John in Corby is asking you this. The moon is moving away from the Earth at a rate of 1.5 inches a year. How long before it has an effect on our tides? Gosh, that's a hard one. What do you reckon?
It's very difficult. It's so difficult I don't know the answer, because I'd have to do a calculation, because we know that the reason we have tides is because the moon is a reasonably big body in orbit. As the moon goes around the Earth, then the gravitational pull of the moon on the Earth can't move that much because, of course, it's a solid blob in space, but the water on Earth is not fixed, so the water can move towards the moon. So what you get when the moon attracts the water on Earth is what's called a tidal bulge. So the water on the Earth's surface facing the moon as the Earth rotates, that bulges, and you get a high tide there. And then on the opposite side of the Earth, directly opposite where that high tide is, you get another bulge, because that bit of water there is furthest away from the moon, therefore it's being pulled less, therefore it bulges a bit, and the bit around it is lower. And that's why you get another high tide on the opposite side of the Earth, and that's why there are 2 high tides a day. So what John is asking is how long before the distance away from the Earth, or how long before the moon has migrated far enough from the Earth before those gravitational effects have decayed to such an extent that we no longer see this attraction of the water towards the moon and therefore tides. And the answer is that I think you'd always see something, because until the moon has completely gone so far away that there's no more gravity field, then there will always be a pull. Plus the fact you've got to take into account the sun, because part of the tides effects is also down to the sun, because the sun also is pulling on the Earth, and that's pulling the water towards it. And that's why you have spring and neap tides, when the moon and sun are or aren't aligned with each other. So in answer to the question, gravity follows an inverse square law. What that means is that if you double the distance between two things, then you get a quarter, for instance, of the strength of the gravitational effect. So if the moon doubled the distance that it is now from the Earth, then the tides, or the pull of gravity, would be a quarter of what it is at the moment, and so on and so forth. So it would take quite a long time before the moon's gravitational effect on the Earth totally disappeared, but we would see a slow diminution of the tidal height on Earth over time. I think, given that the moon is moving away from Earth by about 3 centimetres every single year, I think it's going to be about many hundreds of millions of years, probably 1 billion years plus, before the moon actually disappears from actually causing or being visible in the sky and causing tides and things. So I think we've probably got a very long time left before we have to worry about that.
OK, thank you. Let's get the music on, because another question here, Mike has asked, not so much of a science question, maybe a bit more psychological. Why do some people scrawl their signatures so that you can barely read them? What's the psychology behind this? Now, Mike, that's interesting, because I had to go to the registrar the other day, and there was a scrawl, for a signature, and she went, hang on, I've got a list of these, and the registrar actually had a list of scrawls that she could identify which doctor it was, which I found absolutely fascinating. So, Chris, what's your view on this?
I remember going to a shop once with one of my friends and watching him sign something for a credit card purchase, and I couldn't read or even interpret what the hell he'd done. And he said, "Mate, my signature's so good that not even I can copy it," as in meaning himself. But the point of a signature, of course, is a security device. And until we had chip and SIN, which it is now with the credit crunch, you had to sign for things in order to be able to buy them. Yeah. And the signature being very fast, it's very hard for people to deliver that kind of very rapid movement and do it accurately if it's not their own signature, because that's a very specific muscle program in order to produce that signature, and it's therefore an excellent security device, because when you have to make a very rapid sequence of movements, it's very hard to learn what someone did to make that sequence of movements and get the flow of the text right so it looks right, because when you look at the signature, you're looking at a number of things. You're looking not only at the shape of the pen on the paper, you're also looking at the indentation, how fast the pen travelled over certain bits of the paper, and the giveaway there is how dense the ink is, how thick it is, because when a pen moves fast, you get less ink spread over a bigger bit of paper, therefore the ink looks thinner, whereas when a pen travels more slowly or overlaps a bit of paper, you get a denser impression. So all of these things are very specific and unique to a style of writing, and they're very hard to copy, and that's why signatures are done like that. It was a sort of security device.
So our own built-in thing, if you like. Now, it's interesting the other day, because the same lady, I said, gosh, that's amazing. She goes, I think, she said, we'll get to the stage soon when people, at school, they won't be teaching writing. What do you reckon about that?
Well, I think that's probably unfortunately true. What we see increasingly is people submitting essays and assignments on a computer, partly because it's easier to hand them in, and to be honest, it makes people who have to mark them, it makes their life a lot easier, because some people's handwriting really is atrocious. And as someone who has to mark quite a lot of exam papers myself, I have to say it's really difficult sometimes with some people's handwriting. It might as well be in hieroglyphics, and you have to labour through, picking your way through what they've written. And that means that they may be at a disadvantage compared with someone who can write neatly, because it's obvious what the person who can write neatly is actually trying to say, whereas you might not be able to read what the person who can't write is trying to say, and therefore they can lose marks. So if we do go to a stage where actually typing is the new writing, I can't see that being a major issue, but I do think writing is a good skill to have, and I think it would be a terrible tragedy if people do forget how to write. Having said that, I used to be able to write very, very nicely until I got a computer keyboard and also became a doctor, at which point my writing deteriorated to the point of being dreadful, and I largely put it down to rubbishy old biros, because when you go to sort of hospitals and things, the drug reps give you lots of biros to write with, which have got their drug name on the side. And these are always rubbishy old biros that encourage you to just scribble and write things very, very fast. And you forget how to write nicely. And the best way to write nicely is to have an ink pen. And if you go and buy a really nice fountain pen, because you cannot scribble with one of those, it forces you to write neatly. And as a result, you can actually remember how to write. So occasionally, when I can sort of apply myself, I go and get my ink pen out, and I can still remember how to write, fortunately. But it's a deteriorating skill set, I think, amongst the general population.
Yeah, it needs reasserting, I think. Thank you for that. Now then, John in Clacton says, good evening. I've heard of gas and coal burning power stations that pump the pollution thousands of metres underground. Could this contaminate the water table? John, interesting question. What do you reckon, Chris?
Yes, this is a new approach to carbon sequestration. And in fact, there was a story which emerged, it was published in the journal PNAS, that's the Proceedings of the National Academy of Sciences, USA, a couple of weeks ago. A researcher at Columbia University in New York, his name is Peter Kellerman, came up with the idea of reacting the carbon dioxide, which comes out of things like power plants, with minerals in the Earth's surface. And this chemical reaction then turns the carbon dioxide into carbonate, and carbonates are insoluble and they're solids. They're like the calcium carbonate that builds up in your kettle, and this is a way of locking the carbon dioxide away as a solid so it can't do harm in the atmosphere. In fact, the reaction that he outlined in his research paper was one involving a mineral called peridotite, which is magnesium silicate. So this is silicon, the same stuff that sand is made out of, and magnesium. And when you add carbon dioxide and water to that, you end up with magnesium carbonate and silica, sand. So, in fact, the reaction products are very safe because at the end of the day, carbon dioxide isn't actually that bad. It's only when it builds up to plague levels in the atmosphere it is. It's not something which is going to poison people. The other things that come out of power plants, though, are if you're burning coal, you're going to get things like sulphur, and you're going to get things like partially burned hydrocarbon particles, and you may also get heavy metals and some radioactive components too. So those have to be cleaned up. So if you were to just pump everything for just as is straight into the ground, you could trigger contamination. But as long as you clean up the flue gases, and you can do that relatively easily to get rid of those main pollutants, then locking away the carbon is probably a good idea. And Peter Kellerman reckons from his paper that he can lock up with each cubic kilometre of rock that he involves in the chemical reaction that I've just described, he can lock away 4 billion tonnes of carbon dioxide. That's out of a total production every year of 30 billion tonnes of carbon dioxide. So you don't actually need a lot of this rock to lock away a very big proportion of what we're producing every single year. So it's certainly a viable tactic and probably something we're going to see a lot more of in the future.
How scary is that? Lastly, Gary has said, what would happen if we didn't have tides?
The answer is probably that lots of sea creatures would suffer because there are many, many creatures that are well adapted to the life on the shore. They rely on the fact that there is a wet phase and a dry phase because what this does is it changes the environment in such a way that facilitates their ability to feed, move, reproduce. And if you took that away, then those kind of animals would no longer have a home. So there would be an environmental catastrophe in that respect because lots of organisms would just disappear. Tides are also very useful because what they do is clean up beaches because they expose on the sand things that other animals can eat, and then they come along and wash away any debris and detritus and replace nutrients, which then also mean that other animals that live in the sand can breed and eat and live. So tides do an important job, and if we didn't have them, then I think the impact would be largely one on the ecosystem and the environment. I think we'd probably see lots of animals dying out.
That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.